So, alright guys, today let's do a Lintcode problem. Normally I don't record videos for Lintcode problem, but this problem is very important, but it does not show in Lintcode. Well, indeed it showed in discussion sessions, but it is not shown as a problem. So here I do I will show you in this video. I will show you how to do topological sorting in the Lintcode 127 problem. Let's see what is the problem. So for example, we have this graph. This is a directed graph. This is a directed graph, meaning there is direction. So 0 point to node 0 points to node 1, but node 1 doesn't point to node 0. That's called directed. So with a graph like this, what we want to output is to output 0, then 1, 2, 3, then 4, 5. So as you can see, it's actually layered, very similar to the layer order binary tree traversal. This is layered output. The first output is 0, which is layer 1, then layer 2 has 1, 2, 3, layer 3 has 4 and 5. So let's draw a picture of that. So layer 1 have 0, layer 2 have 1, 2, and 3, and this layer have, and by the way, they are directed graph. This layer has 4, which can come from either 1 or 2 or 3, and this layer have 5, which can come from either 1 or 2. So this is the graph. So what should we do for topological sorting is we should do topological sorting in 3 steps, always 3 steps. So the first step is to collect in degree information of each node and store the information in a dictionary. So in this dictionary, the key is node, while the value should be the in degree value of that node. Okay, so that's step 1. And step 2, I will explain what is in degree information later. Step 2 is to collect the neighbor node for each node, the neighbor node for each node. So for example, for node 0, the neighbor node for node 0, the neighbor node should be 1, 2, and 3. For node 1, the neighbor node should be 4 and 5. Which means 1 can point to 4 and 5. Okay, each node, and store them in a dictionary, of course. And in the dictionary, the key is node, while the value is really an array of all the neighbor all the neighbors of that node. So collect neighbors. So step 3 is then do topological sorting. Sorting, meaning we should use BFS to store the nodes dot value layer by layer. So always 3 steps. So let's explain the first step. Collect integrity information of each node. So that means, so integrity information really means of an integrity information of the node really means how many nodes this node depend on. For example, let's take this for example. Okay, say node 0, this node doesn't depend on any other node because no any other node point to this 0 node. However, for node 2, so the integrity of this node is really 0. Is 0. For node 2, however, since there is one node pointing to 2, so the integrity value for 2 is 1. So what about for node, say node 5? For node 5, there are 2 different nodes pointing to node 5, so the integrity value is 2. For node 4, since there are 1, 2, 3 different nodes pointing to node 4, so the integrity number of 4 is 3. So we collect all the integrity informations and store it into a dictionary. And the second step is to collect all the neighbor nodes for each node. For example, if we want to collect the neighbor node for say for node 5, then in that dictionary the neighbor 5 should have the node 5 should have neighbors pointing out, which is basically none. So however, for say for this for node say 1, okay, for node 1 the neighbor should be 4 and 5 because node 1 can point to 4 and 5, so the neighbors for node 1 is 4 and 5. Then we do topological sorting. We use BFS to print or store the node value, layer by layer. So okay, so let's try to implement this algorithm. First thing first, let's do edge case, graph, return, empty array. Firstly, let's do step 1, which is to collect integrity information of each node. So and store it in a dictionary. So say integrity is the dictionary dot default dictionary. Since the values of this dictionary is integrity value, so it's int, so we use int. So integers equals, let's use a subfunction called get integers graph. So let's figure out how to write that get in degrees function later, but currently let's just focus on the main function. So that's step 1. Step 2 is to collect label nodes for each node and store them in a dictionary. So which is already done because we can which is already done in this class. So in this class there are self.neighbors. So that's already done. So that's good. So let's do step 3, do topological sorting, layer by layer using BFS. So in order to do topological sorting, we need to use a queue. First thing, let's say result equals, and we need to use a queue. So queue equals collections dot dequeue, and for the what we want to append to queue is, firstly we append the ones that has 0 in degree value. So for node and in degree in the dictionary of in degrees dot items. Okay, so if in degree equals 0, then q dot append node while q. So in BFS we should always remember that in while loop we always want to do two things. Okay, so the first thing, can we change the color? Okay, you cannot change the color, but anyways, let's just do it. So we should always, in while queue, we should always do two things. The first thing is to deal with the current layer, and then the second thing is append neighbors to the neighbors, or we say the next layer. Okay, so let's first deal with the current layer and then append the neighbors, or append the next layer. Deal with the firstly, let's deal with the current layer. So in the current layer could have more than one element or more than one nodes. For example, for this layer there are 3 nodes, so we say length equals length of firstly let's say current node equals q dot pop left. That's the result. Then should append current node dot value, or just current node, and then deal with the next. So that's how we deal with the current layer. Then the second step is to append the labels. So for label in current node dot neighbors. Okay, so the in degrees of neighbor should minus equals 1 because it's visited. So if in degree neighbor equals 0, then we should q.append neighbor. Maybe it's not very easy to understand this sentence. If in degree neighbor equals 0, so this sentence really means, say take 4 for example. Let's take 4 for example. Okay, so if the neighbor is 4, so when we visit 1 at the previous level, so the in degree, so when the current node is 1 here, so the label, so it visit label which 4 is one of the label, so it will visit 4. The in degree of 4 will minus 1. Previously it was 3, then it will minus 1 equals 2. At this time we don't append 4 into the queue, because at this time if we append 4 into the queue, then when we visit node 2, the label 4 always is also a neighbor of 2. So then if we append 4 when the in degree is 2, when we deal with node 1, then we need to append it again when we deal with node 2. Then we need to append it again when we deal with node 3. So that means we will append 4 into the queue for 3 separate times. That will lead to duplicate append of nodes. So what we do is we always append when in degree goes to 0. For example, when we append so we only append when the in degree value goes to 0. When we deal with node 1, so the in degree minus 1 equals 2 now, minus 1 equals 2 now. Now we go to when we go to node 2, the in degree of 4 with minus 1 again equals 1. Then we go to in degree 3 and find that 4 is also its neighbor. Then we get the in degree of 4 minus 1, which equals 0. And then at this time we append 4 into the queue. So in that way we can avoid appending this node 4 into the queue 3 times. So this is how we avoid that. So remember, always append the neighbor only when the in degrees of this label equals 0. Okay. So that's how it works. I think we can just simply return result. Let's see. Oh, there is a subfunction we need to define. That is to find the in degree. Define get in degrees rough. So we define, so all the in degrees should be stored in a dictionary. Int. So firstly we initialize the in degrees dictionary. So for node in graph in degrees node 0. That's initialize for node in graph. Then for neighbor in node dot neighbors, then integrate node plus equals 1, then return integrate. Okay, return integrate. Then we run test. What's the output is empty. Why the output is empty? Okay. Oh, the edge case is implemented wrong. Oh, 4. Result should append current node. Current node dot neighbors integrates neighbor -1 equals 0. Then append neighbor. Didn't find anything wrong here. Let me see. This is weird. I think the algorithm works pretty well. The algorithm should work pretty okay, I think. Okay. Okay, here let's print in degrees. Let's see. Dictionary. What is that? 4. 2. Object. That's 4. That's 2. That's 2. That's 1. That's 0. That's not true. Oh, not node +1, but neighbor +1. Oh, neighbor +1. Okay, okay, I see. Not node +1, neighbor +1. If it's node +1, that means, well, that means something wrong. That means, for 0, the integer is 3. But for 0, the integer should be 0 because nothing points to this 0. So it really should be neighbor +1, yes. So let's try to run that test again. Should be fine this time. Okay. Okay, now it got accepted. So that's topological sorting for today. Remember, there are 3 steps for topological sorting. The first step is to collect in-degree information for each node and store the information in the dictionary. Well, in the dictionary, the key is the node, while the value is the in-degree value. It should be noted that the in-degree value should be while we try to implement the get in-degree function, we should say the in-degrees node in-degrees neighbor plus equals 1 instead of node plus equals 1. Okay, so that's why we made a mistake a couple minutes ago. The second step is to collect the neighbor nodes for each node and store them in a dictionary. Well, in this dictionary, key is the node, while the value is all the labels of that node. Then we do topological sorting. Actually, it's just using BFS to store the node layer by layer, and we should remember that only when in degree equals 0 do we append the neighbor. Okay, so that's all for today. Also, in real interview of Facebook, there is this follow-up question, and the follow-up question is, what if the topological order does not exist? Then how to tell whether or not it exists or not. For example, we have a graph like this: 0, let's say 1, 2, 3, so 1.0, 2.1, 2, 1.3, 2.3, and say what? And say 3.4, 4.21. So here we have a loop: 1.3, 3.4, 4.21. So if we have a loop, then in doing the topological sorting, we will find that the length of the result we are going to print it will be larger than the length of the graph, because we got more in-degree informations. For example, in this in-degree -1, so the in-degree informations are more complicated. Let's try to figure it out. So the in-degree information for, say for example, for 1 is 2, so that's 2. In-degree information for 3 is 1. In-degree information for 4 is 1. In-degree information for 2 is 1. Okay, so when we do traversal, we do 0 first, then we do 1 and 2, and then we do 3 and 3, then do 4. After we do 4, we do 1 again. So that is why the length of result is larger than the length of graph, because we do 1 again. So we append 1 really twice. So if the length of graph, length of the result larger than length of graph, then we should return none, because it has a loop. It's not the topological sorting does not exist. If else, then we just return the result. So it is very important that if the length of result is larger than the length of graph, that means topological sorting does not exist. That means topological sorting does not exist. No exist. Okay, so that's all for today. Thanks for watching my video. This is a physicist trying to lead code. If you are similar with me, coming from physics, biology, chemistry, civil engineering, or other non-CS major, please join me together and try to solve Lintcode problems and try to find your dream job together. But what you can do right now is to subscribe this video or comment on this video, and we can make friends start from now on. Thank you very much. Okay, bye bye.